Okay, this is the last lecture, or the first, depending on how you think, where we really start to begin to use the wave and oscillation stuff to understand relativity and quantum mechanics at a deep level. Today I just want to finish up and maybe do some things that we went through pretty quickly last time, and that is just to look once again at the two-dimensional oscillator, the whole idea of the 90-degree phase lag, and in particular the thing that will make us or break us in the discussion of relativity and also quantum mechanics when they're put together the way we do. This thing I call a half-sum, half-difference identity. We're going to do the geometry of that in class, so the next homework assignment will be done mostly in this room. And that is the key piece of algebra and geometry that makes it possible to really understand the relativistic phenomena, relativistic quantum phenomena. So we'll go through this B-type oscillator again, and then the way I'm approaching it here can be extended to 3, 4, 5, 6, 7, 8, 9, 10, as Gamow used to say and used as a title for his book, 1, 2, 3, infinity. There's a lot of things in physics and mathematics that if you could just get to the third order, the infinite order becomes much clearer, and sometimes becomes exactly the same, and that's what's going to happen here. So the formula that we'll be developing at the very simplest case here is going to work for all of the waves that you encounter in this particular type of description, this resonant description. So I hope to do most of our work in this neighborhood with a hexagonal oscillator. And then next class we'll be taking that, the infinite version of that, very seriously. So once again, I'm going to make sure as best I can to keep these two screens in sync, and use applications, the apps for animation from both of them. The thing that we were talking about last time was the connection between a matrix that we call the K matrix, which describes classical two-dimensional oscillator, and the more fundamental one that is basically an isomorphism, that is a mapping, a direct mapping of the classical one to the quantum mechanical so-called Hamiltonian tunneling matrix is sometimes what people call this thing. In any case, a matrix that just consists of two parameters, one of them being the coupling and the other one being the whatever it is that gets each one of the individual oscillators oscillating. So the key here that I want to try to get across today is that if you just look carefully at some symmetry group theory, some of the stuff that we've talked about a little bit, you had a homework problem that most people did pretty well after some effort that involved a six-fold symmetry. We're going to see that again here shortly. But here it's just a two-fold symmetry of the B-type, bilaterally balanced symmetry that has a multiplication table that looks like this. And that is that the unit operator times sigma b is sigma b. It's pretty trivial. And then sigma b times the unit operator. This is a commutative or abelian group, so it's always pretty much the same elements on either side of the diagonal. But the idea is to take a group table, a multiplication table, a product table, and turn it into a Hamiltonian. And that's cool. That's basically an invention of this laboratory. This was only recently published, so it's something that is going to make it a lot easier to learn group theory, but mainly it's going to make it easier to do physics as well in some pretty interesting ways. So at this point, we're really only talking about a very simple equation that can be condensed from this product table, and that is that this particular matrix squared is a unit operator. So this thing with an I on it is a crazy thing, which can be, as we talked about at the end of the last lecture. Now, what I want to make a point of is that once you have this multiplication structure, you have all of the sort of interactions that occur caused by this Hamiltonian. You also label each of the base states for this behavior, that is, the dimensions, you might say, of this system. In this case, an x dimension, if it were a two-dimensional oscillator that operated in an xy plane, the x would be this thing that I'm calling 0 here, and then this other one, number 1 here. The idea being that this system that we're talking about, either this one or this one, is a binary system. That is, this would be the basic classical bit that all of our computers now are built on. All of the operations that we do are inside the computer are binaries. Frankly, we don't have to look at that unless you're a programmer at the deepest level, but that's what's going on. And the quantum computer is going to be made of what are called qubits, that is quantum bits, which is described by this system of matrices and operators and whatever. In any case, this is 0 mod 2 and this is 1 mod 2. That's the way you would describe it. We're going to talk about numbers modulo other numbers as we go through this, because that's what sets you up to do the general wave picture. In any case, there are two states here that form the basis for all of the motion, and one of them has this mass moved over by 1 unit from its equilibrium position. So we call that the x state if we're doing an xy picture. I'll call it 0 mod 2. And then there's the 1 mod 2, the number 2 state, if you were going to just number them 1 and 2. That's not what we're going to do. We're going to use the arithmetic that works best for this. And that is a state where this one sits on the equilibrium like this one was, but now this one is the one that's moved by 1 unit. So the vector here indicates the x and the y components of a two-dimensional oscillator, but this notation here is the thing that I want you to get used to. And there's several things going on here that are important. First of all is that we're going to label the states quite often just by writing the name of a particular operator. That's the reflection operator, the bilaterally symmetric reflection, a mirror reflection that reflects x into y and y into x, or x1 into x0 and x0 into x1 states. So that is the basic idea here, starting from an equilibrium state where you have 0, 0 for x and y. You get 1, 0 and 0, 1. That's the basis of the physics of all of the motion for this system. So very simple thing, but the idea is that it generalizes to some really cool stuff. So we already talked about how the other way to write that equation is that the operator squared minus 1 equals 0. Any binary operator is going to satisfy that, and then we factor that. Binary operator plus 1 and binary operator minus 1 equals 0. And those are the two unnormalized projectors that we talked about last time. We're going to use that again here. But first we normalize them. And this is the grown-up projector that satisfies a very simple relation, namely orthonormality. That is, they're orthogonal to each other if m is not equal to m. If they are equal, then the product of these two operators just gives this operator back again. You need that 1/2 in order for that to happen. You also need it in order for these two to add up to 1. It's very trivial that they add up to 1 here. This subtracts that. and you're equal to 1/2 plus 1/2 times 1.
All right, everybody memorize that or take a picture of that. That's what part C on your homework that's due Thursday.
Yeah, your homework is just based on doing this sort of thing with
Like
operators that are
four
binary.
lines, exactly.
Yeah, that's a good point, Al. So, and take a picture of it real quick. That's easier probably than going to the website, pulling it down. But remember, this whole lecture slides are on the web, so you can get the picture fairly easily. Okay, let's go ahead on this one to this point, and the next step is to look at the modes. Okay, and the modes are gotten by simply applying the projection operator to the first state. The first, or it should really go the 0th state. This is like to count 0, 1, 2, 3. So do people that do C programming. The 0 is the beginning of everything. And then 1, and finally 2, 3, 4, 5, up to n. That's what we're going to be talking about there. In any case, we have a unit state here, and 1 times that is very trivially that. Then the reflection operator gives us the other state. So it takes this distorted motion and puts it on the other side, and that makes the other state. That's the way to think about the group operator producing the states. So I then can take a projection operator P plus, that's a half sum, and take this plus this 1/2, and I get a motion that involves these two together. Okay? And I can do the opposite one. I can take 1 minus that half difference and subtract that state. That means it's coming in instead of going that way. And I get the high frequency mode for this this motion now. You should also notice, and this is an interesting sort of thing, that if this is the kind of molecule that you breathe, like oxygen 2 or nitrogen 2, okay, this is the only mode of vibration that you have. This is just plain old translation. This is a 0 frequency mode right here for an oxygen molecule. Imagining it's confined to just one dimension and can't rotate. Rotation is a whole nother symmetry that we're keeping out of the picture right now. We'll get a little bit of that before we finish this course. But that is an interesting thing, because this equation right here for an idempotent operator, P squared equal P, is also P squared minus P equals 0. And that factors into P minus 1 and times P, right? So one of those P's has a 0 eigenvalue that's tossed away, and then the other one has the actual vibration that's keeping you a little bit warm today in this room. That most of the warmth that you feel in air is due to vibration and rotation, actually. Together they pretty well account for the thermodynamics of the atmosphere at low temperatures, medium temperatures. In any case, this is sort of the professional way to write the kets that are eigenkets of this operator. And I see a typo right here. This should be 1 modulo 2, and that should be 0 modulo 2. I keep getting those nasty things. Okay, make a note for that one.
There's one little time.
In any case, we'll be seeing plenty of things where this is done correctly, but this one was so trivial I just copied and pasted and then forgot about it in a microsecond. So what we are really looking at here, and these are the kind of tables that you make out of all of this. If you just write that table for somebody that knows a little bit of group theory, they say, aha. And where you won't see in the literature, you won't see Phaser describing, but this is what you would get if you look up the group C2 on the web. Yes, for cyclic 2, 3, 4, you're going to get the tables we're going to calculate today. Those are called character tables, and they're very important for doing the kind of quantum mechanics that, well, information age is going to be requiring us to learn about. Now, one of the things that's important is that if you just deal with operators, if you let operators do all your labeling, and you let the operators make your Hamiltonian, this is just a linear combination of the two operators that are describing the symmetry here. If you do that, you never have square roots, whereas if you must insist on working with the old-fashioned kets and bras, now they seem old-fashioned, they were very modern when they first came out, that is the case here. If you're talking about states and kets, it's 1 over the square root of 2 times the 2 base states. But if you're talking about operators, it's just a half. You don't have to mess with square roots, and that can save a good deal of arithmetic as you get more complicated here, which we will do shortly. Okay, so that's C2 sort of in a nutshell as a sort of notation here. And you see what we're doing here is we're using the operators to both label positions or states, and we're going to be using them to label transitions, that is motion. And that's kind of what's going to make it possible for us to do some stuff that's pretty powerful. Now, this half sum and difference that I'm making big fusses about, this is where it starts. This is where you see it. It's almost too trivial to notice at this point, but it's very cool later on for all sorts of things. Okay, now let's just review when the 1, 2, 3, 4 matrix that we used to make our projection theory that didn't have anything to do with the Hamilton operators, the Hamilton quaternions, the Hamilton spin-half spinners, whatever, all that stuff that's kind of got letter sigmas associated with it. Let's just go back and suppose that I had a K matrix and this was just a classical problem, and here are the spring constants for that K matrix, and let's just make it simple, 10 and minus 1 for this number right here and that number right there. And go ahead and write the secular equation for this matrix. And remember, that is a very simple form of the secular equation with 2 by 2 matrix that involves the so-called trace of a matrix. And the trace of the matrix is simply the sum down the diagonal. Okay? So we're talking about 20 here, and it's minus the trace, so I have a minus 20 here. And then the determinant, very easy, it's just 10 times 10, 100, and then minus the product, which is 1 in this case, for the counter diagonal. Okay, so that's 99. So we have a equation to solve here for the eigenvalues of the K matrix, which has K squared minus 20K plus 99, and it factors very nicely into K minus 9 and K minus 11. So those are the eigenvalues that we're looking for right now. We'll call them K1 and K2 for this problem. But this problem isn't any different from the one we just looked at. It's a B-type symmetry. And if you're going to go back and look at the problem from the quantum mechanical point of view, where the eigenvalues of the Hamiltonian are the actual frequencies, here's what you would get. Here our eigenvalues are 9. That's the square of 3, so 3 is one of the eigenvalues, and then the other one is the square root of 11. This is omega squared equal 11. So at this point, if we're just going to do classical mechanics, our eigenvalues are all plain old integers, but the quantum mechanical one's going to have a nice little square root of 11 in it, and that we'll see showing up later when we make a comparison here. But in any case, without knowing the ABC theory, just that basic idea of breaking a matrix down into its projectors, remember what we do is for projector 1, we take the matrix that we have and subtract the other eigenvalue from it. In this case, the other eigenvalue is 11. So I take that matrix and subtract 11, the unit matrix times 11, from the original matrix. And that gives us, well, surprise, it gives us a projection operator just like the one that we write down from the symmetry that this particular one has. So there's your 1, 1, 1, 1 projector, the symmetric projector, and then you do just the opposite on the other one. You subtract, to get number 2, you subtract the eigenvalue for number 1, namely the 9 is being subtracted, and surprise, surprise, there's the other projector that we just looked at from the symmetry point of view, okay? And it helps to see as many different ways to do a problem, because it reinforces your, first of all, the knowledge of what's happened, but it also makes connections, you say. And it's that when you weave those connections into your head, you become much better at remembering what's going on, but also able to do some creative work with whatever we're doing here. In any case, may I make the point that I have here a vector with a 2. If I want to play the Ket game, the kind that you will play if you take the quantum course, then I need the square root of this. So I need 1, 1 with a square root in the denominator, and I need another 1, 1 with a square root in the denominator. And those two outer products make this matrix. You see, this is factoring a matrix so you can get back to the old-fashioned way of displaying a Dirac-Ketrel. Same thing with that one, except you have a minus sign here. And so that number, actually the number that sits on the diagonal, and it'll work for either this column or that one. You use either one to, because these things will still work if you multiply it by an extra phase, like a minus 1. So that is the set of projectors that will take care of this. And I want to show you how a projector is used for setting up motion. Basically what you do is you take the sum of the projectors, which by the completeness relation is 1. Remember those, when I add these two things right here, I just get 1. And that's one of the tests of your projectors. And I take this and I'm going to multiply it by some initial state. Well, what's the initial state that we like to work with? Namely 1, 0. Okay? So that's what is going to happen here. And when I do that, I set it up so that I immediately get a linear combination, in this case half and half, of the two eigenstate, the symmetric eigenstate where they're going together, and the antisymmetric one where they're at a loggerhead, so to speak. So I have, this would be the professional way, a quantum mechanic, as opposed to a graduate mechanic, would put the numbers that reflect the square root of 2, 1 over the square root of 2, for each of the two vectors. Now, at this point we say, okay, what's going to happen when time is not 0? When time is not 0, I'm going to get E2, the frequency, omega with a 2 or omega with number 1 here, as the argument of the exponential. So that's the way you get motion going here. You take this thing here and just put whatever frequency goes with this one in the exponential. So this is the phasor for this one, going at an omega 1 rate clockwise. Okay, well, it's not clockwise just to keep the arithmetic down, or the size of things down here. I'm doing the old engineering phasor right here, a phasor that goes with the right hand. Okay, presumably they're more either right-handed or right politically, I don't know which, but let's just do it that way here. And so this is the equation that you would get if a typical engineer using phasors were to write it. And it isn't that important right now that we keep that minus sign. So what I'm getting here, when I add these two together, is a sum here of two exponential phasors going at different speeds. Omega 1, omega 2. And omega 2 presumably, usually, is the high frequency. Omega 1 is the lower one because we're not pushing a coupling back and forth. So that's where this comes in. This is the thing that's going to save our bacon in so many different ways. What we're going to have to do is factor sums like this. And this is an easy job with exponentials. So rather than spend a good quarter of a period doing the usual thing, we just write it down, write the answer down. And you can see what this trick has done here is I'm taking these two and doing the half sum of A and B that's what's written right here, 1/2 with an I on it. That's e to the I 1/2 a plus b. And multiplying it by 1/2 of a minus b. That's getting me this term right here. And then I add to that with a negative sign. That gives me this term right here. And then I look at it and I see that this factor here is real, a real number. This is a cosine of a minus b with a 1/2 sitting in front of it, just like it was in the original thing. So, and I can do this for this top part right here, and for the bottom one, which is a minus of these two. For the bottom one, it's just coming out to be a minus sign here instead of a plus sign there. Same trick though. I've factored it into a real part that serves as an amplitude, and then a phasor part that serves as the phase. Is this making sense? This is so key too, because in every piece of work that has quantum mechanics, there are two very important pieces of the any sort of equation or solution, and they are the amplitude. How big is the phasor? Which, when you scare it, gives a probability. That's something you learn, and we'll be proving that later on. Or the where the clock band is. That's the phase. And this cleanly separates this sum by factoring it into a cosine in this case, and a sine with an I on it. That's because cosine phi is just half of the sum of the exponential and the counter exponential. And the sine is, and once again, I see, I put a note down for that minus sign that should be there for the sine of phi. But the I is definitely in the denominator for it. So this one right here with the minus sign becomes a sine function, and this one a cosine function. And that's the thing I want to look at in the animations. I want to see this once again very clearly. I also want to look at the geometry of this. I mean, this is the guts of everything that happens in quantum mechanics. They say quantum mechanics isn't sexy. Yes, it is. This is where two phasors get together and make something really weird. Okay? This is it right here. This is what once you understand, then a whole bunch of things become available to you. Okay. Now, that's something we'll be, as I said, animating shortly here, but I wanted to make sure that you see it. We have a couple more things I want to say about this, but this is really crucial. This is the heart of the whole modern physics, you might say, that we have now. The breakdown between the phase and the amplitude. And both of those have an uncertainty associated, and we're going to talk about that later on. But that is really crucial separation. It's very clean and very important. Well, anyway, here's the actual picture of the old program giving some animation. Here's a bigger picture of it. And the thing I would like you to see right off the bat is the amplitude is a cosine. That's this thing. That's the thing that gives you the beat. So that is sort of the outside of this wave that's multiplying this one, and then this other one right here. This is the cosine one. This one right here is multiplying the phase with the sine. Okay, so here's your sine, but the sine has an I on it. Note the I. Okay, that's key, because I is e to the I times pi over 2. E to the I times 90 degrees. This thing is attaching an extra 90 degrees to the phasor that's making this wave beyond what this one has. And you can see this one starts at the top and comes down. This one starts at 0. Well, that's our initial condition, right? And then grows. And always this is sine-like and this is cosine-like. If the amplitude hadn't been there crushing it. This has just been allowed to expand, and this one will keep the same amplitude. You just have a cosine and a sine here. A sine being being out of phase, its actual phase, would have an extra 90 degrees attached to it. So get some animations to show that, so you can really see it, and also see the geometry of why that has to be. This is goes back to 6th century before the Common Era with Thales geometry at work. Okay, so maybe on this screen here we'll go ahead and actually run this animation at various speeds, namely slowly at first so we can see some of this stuff. And then I'd like to talk about some of the number theory that comes with any sort of wave like this, where you do continued fractions to see what kind of symmetry, internal phase symmetry you have. The thing is a symmetrical pattern there, but not quite. And we have to discuss that because that's something that's going to be coming up in quantum information theory. You might as well get used to. It's quite beautiful, and so we'll do that. Now let's see if this is going to work. I'm going to start this simulation and show you how to run. The first thing I'm going to do is slow it the heck down. So I'm going to drag this thing back here. That's one way to slow it down. The other way to slow it down is just go in here and change the exponent to something that's a little more negative. That brings it almost to a stop. Okay? So this is slow enough that I can talk about it and not have it really. You'll notice there's a 90-degree phase lag between these two. This guy right here is ahead by 3 hours if this was a 12-hour clock. It's going through 3 o'clock when that one down there is, let's see if I've got this right here. Yeah. This one is ahead by, I think, let's see, do I have the thing going the right way? I want to make sure I've got everything with the right sign on it. And now it's just hitting the low point here, and the other one is at its peak. That's this one right here. Now it comes out, let's see where this one is. You'll see it right there. Let it swell out a little bit so that the arrow actually shows. I was wrong before when I said this one was ahead. It had already gone through the cycle. Now this one is the leader. Okay? Now this one is at 6 o'clock when that one's at 3 o'clock. I had the reverse before. That's what was going on this side. But now this one is giving to that one. Remember when I said that the phasor that leads gives? The phasor that leads is the donor, the poor little one that's receiving the largesse of this one is late. Okay, late by exactly a quarter of a cycle. And that maintained until this one has given its all to this one, which will be happening eventually here. But you can see how the progress is over on the time graph. Now let's start it over again, just to make some more points that are important for this. I'm going to reset t equals 0, automatically erases, which is nice. We got that feature. So they start off again. Okay. Once again, this one had nothing. Can't even read its phasor yet. But when you do get to read it, it should be coming out fairly soon there. Yes, there it is. This one now is approaching 9 o'clock. That one's approaching 6 o'clock. It's 3 hours behind. You see. Okay? Now what's this one doing? At first it's just sort of drawing a line across, and then it's developing, well, some area under this one, which could be thought of as force versus position, because whatever this thing has as amplitude is turning out to be force for that one. So this is a work cycle actually being plotted here for work done by this guy right here on this one. And the idea is that with the right-hand rule is positive work. That is, the area under that curve, and that counts this one too, is all positive. And it's growing as fast as you can get, because 90 degrees is the best that this one can do in terms of getting energy into the other one. So this one is growing and very quickly approaching, and that's the other point I want to make, is that what we're looking at here is really an important part of optical polarization. If we're thinking about this as a theater of a laser beam coming at you, there's a polarization, say, in the X direction, and there's a polarization in the Y direction. Those are plane polarization. This is what most commonly you see. But what we're going to do is show all possible polarization with this sort of picture here. So what I'm going to do is I'm going to make two changes here. And while I'm going to go ahead on this thing here, just to point out where some of this stuff is. I'm going to jump ahead here to something that has a listing. I'm going to jump quite a bit ahead here, I think, because I really should have put these control features up front. So here's what I did. Here we go. In the control panel for this thing, you have a number of options for all of these waves that we're going to do today, and for the rest of the course for that matter. The three options that I have right here are available on this part of the...
You've got one for box it, one for wave it.
Let's see if I go ahead and... yeah, you're right. Let's see.
Yeah, there are two primary apps for today.
This is wave it right here. Let's see. This is box. This is what I want. Let me go ahead and point out. First of all, let's see if I can. I should have put this thing.
We don't have a tutorial page for box it.
Yeah, that's true. This is wave it thing. I'm very sorry. I mixed up these two applications in my head. Let's just go ahead and do it on this one right here. This is the thing I want to describe right now, so we'll go ahead and do that just on this particular animation right here, and then we'll come out later and do it for the fancy ones. Okay, so on this one I'm going to let it go pretty fast here, but I'm going to make some changes. First of all, I'll not print the fractions right now. I'll simply do this thing right here so that we can point that out. But I'm also going to make the coupling here quite a bit less. Let me go ahead and make something like, I'll see how well I can get this number in there. I'll go 0, 3, should be, whoop, didn't work too well, 0.3, but I don't want that, I want 0.3. I want to really make the coupling slow, like it is in optics when we're talking about polarization. These things occur very slowly, and I do want to minus so that it's doing everything that's the same as what we had before. And I'm going to bring the speed down here. Well, I'm not going to bring it down. I'm just going to let her rip. Let's see what happens. There we go. So we start with X polarization, and then let me get this thing on the pause button here. At about this point right there, I stop, and I now have right circular polarization. That's right-handed is positive in everybody's way of thinking in science, and it's on the positive C axis with this a little thing we call the Stokes vector. And remember, this is something that was invented in 1867, so you know, we should be up to this by now. And then, as this continues, then it starts to work its way through to finally being Y polarization, which is the orthogonal polarization to X polarization. And that's about it, if I can catch it, right about there. I went a little too far. You can see the spin vector is just a little bit past the minus A axis. But the A axis is the axis that has on this end the X polarization and on this end the orthogonal Y polarization. And that's the beauty of this wonderful space. All of this complicated stuff is replaced by a single dot going around in a real space. All of this is complex spaces over here. This is a heck of a good way to understand what's really going on with the spin system. And to talk about it. In other words, you develop a vocabulary for the three-dimensional real space, which lets you think up things to do with all of these weird oscillators. So I wanted you to see that just to get a feeling for what's going on. And as it continues, you see, one of the things that happens is it's just going to go through the whole thing again and bring that Y back to X. And we might as well just try to do that. I wanted to show one other thing. Remember, we started over here, and this is a real hat trick that I want to see here, and maybe later we get to talk about that in some detail. But there's the left circular polarization, the orthogonal to the right circular we just passed, and now it's starting to deflate into X polarization, and I'm going to try to pause right there. It's not quite there, but the idea is that at that point, this diagram is not home yet. It's minus, has a minus phase on it. It doesn't quite come home at that particular point. And when you learn your quantum mechanics for the first time, they're going to be throwing at you a space like this, and they're going to call this the spin-up axis, and this the spin-down axis. And you should ask the professor, hey, that isn't down. Down is over here. If this is up, that's down, right? But that's true in this space you live in, but not in this space. When you get the spin vector all the way around 360 degrees, you will have only gone 180 on the phasor space, and you'll be here. That is really deep. That's really an important piece of understanding what space and time are about. And I will say more about that later. But, well, let's just drop it at this point. It's just something to be mystified by, as if you didn't needed any more of that. Now, at this point, I want to go over here. I think maybe I can go on this one and do it. I'm going to go ahead and disconnect that little piece there. But I would like to look at not the difference between the two eigenfrequencies, but the ratio. What is the ratio? In this case, it's an irrational or near irrational number, and so that's going to have effects. And I also am going to slow things down a bit here to make this work. Let me just bring the speed down factor 2 here, see if that works. Okay, now I'm going to erase the paths. I'm going to reset time equals 0. There we go. And we're going to go ahead and print, and let me see if that's even the right numbers that I want. It looks like it's not. So see what I've got here. 303. Yes, it's a little off because that should be 0.1. That's what we get for changing things. So what I'll do is I'm going to switch this guy back to the text, and we'll do it over there where I haven't messed that particular thing up. Okay, let's go here. And what I want to look at right now is that, and I think I've got the right numbers in there, do I? 3.17, yeah, that's the square root of 11, so those are the right frequencies. And that's the continued fraction that those numbers give you if you do their ratio. So let me bring this forward and discuss continued fractions. This is some arithmetic that you really are going to have to learn if you're going to stay in the quantum information business. Let's go to something everyone knows about. Recipe for continued fraction approximation, a good old 3.14159265. Okay, that's as far as pi I want to go right today. And do the first thing that you think to do to that, that's take the integer of this number, that is, throw away the decimal. You get 3, which is in 2 places in the Bible. The pi is actually given as 30 cubits around for 10 cubits across. And that's the correct value biblically. But we know this is a... But let's approximate. Let's see how it looks on the next approximation. Okay? And what you do there is you take this n0 and subtract it from this one. That gives you this number right here. And you do the inverse of that. Okay, so you get a 7.06. And you take the integer of that. And that's what you're going to add to 3 to get what the approximation would be at the first go-around for this continuing of fractions. 22/7. That's pretty cool. Okay? So it's these ratios that we're going to be looking for as we approximate a frequency ratio more and more and more by a decimal. Okay? In this case, you get 3.14. Well, that's really good. With 3.14 and 1 rounded up to 2, we already got 4-figure accuracy for pi. Okay? And as you go through this thing, the bigger the number that you get here, the bigger the jump in precision. I do it one more time here, you see, getting an n1 and then subtracting that from there, which gives me, and then inverting it, which gives me a 15. That's 1 over 0.06, whatever this one was. Okay? And I take the integer of that and add that. That's why it's continued fraction. This thing is a fraction, and I add that as a fraction to the denominator of the 1/7. Okay? That's a number like that. Look at how good your approximation is going up 2 figures. Okay? And so forth. All right? Now there's some numbers for which this is really inefficient. This pi is fairly rational. This one is not. This is the most irrational number that you can have. We talked about this golden ratio when we were talking about perspective a little bit. This procedure here, using that 1 plus the square root of 5 over 2, it's an amazing number that is so that when you cut a golden rectangle, you get a square, and then you cut it again and you get another square, and so forth. That was what we were looking at before. Well, here's the arithmetic of that. The very first approximation, of course, is 1. That's not very good at all, but we're going to make it better, or at least try to. And when we take the integer of that one, we get 1, so we get 1 plus 1 over 1. Okay, 2. Well, that's not much closer. In fact, it's on the other side, right? So you keep doing that, okay? And once again, when I take the this one right here and do the same thing, that is the A0 here minus the 1, then I get 0.61. To do the inverse of that, that happens to be the golden ratio, and that's the property of the number is really that. And so, well, I'm going to be going back and forth, making lousy approximations forever, and the continued fraction will just be a bunch of 1s forever and ever. And already here, when we were having nice 9-figure precision up here, we're near, we're barely 2 figures, right? So this is really irrational. This is a number that I use in all my simulations when I don't want people to ask, what's that pattern that you're seeing in the XY plot? Because it won't make one. It refuses. It's the kind of thing that you get, the kind of pattern that it will finally make are the kind of patterns you see in flowers. like sunflowers and things like. Your eye will spot spirals, and all those spirals will be ratios that approximate the golden ratio. So it's golden in the sense of the sunflower in some ways. Now, what do we have here is a square root of 11 over 3. Okay, 1.10545. So I apply this continued fraction thing to that, and I'm building here, well, 10 ninths, and then 21 19ths. That's as far as I need to go here for what we're doing today. What you will see when you do this is if you let the thing run just a short period, and I'm going to see if I can get that one back again over here, because it is really quite spectacular. Let's get this one going again. There we go, and I'm going to try to pause it. I should have stopped right there, and I didn't. Let's reset time equals 0 and slow this thing down. And I'm just about there right now. I should have stopped right there. Let me try. Do it again. Reset t equals 0. Get my cursor on the button. And I want to stop it when it comes to the bottom. And very close to the bottom. Stop! Oh, it slipped. Well, one way to do it is to back up. Well, I can't do that because I won't erase. Start again. If I could just reach up there and grab it, I would probably not miss it, but when you got a mouse in your hand, they're kind of squirrely. There, we'll just stop right there. The ratio, which is the number of cuts on the low speed line. This is a low speed axis. This is the high speed. Remember, beginner slope, advanced slope in Bear Valley. The fast mode axis is cutting this thing 21 times for 19. If you just count across going on the red line here, what you do is you have a 1 there and then 2 right there. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There are 2 ones there. So there's 21 cuts across this one, while this one is only doing, and you can count them yourself, 19. So that is this particular continued fraction. The next stop, this thing's practically black. It's 199 over 180, and after that, it's roughly a little bit like, well, 220 over 190, but this is what it would do as it tried to make this thing finer and finer and finer and finer. As you get finer and finer pixels, you ask for patterns that have enormous symmetries, 859 symmetry. Okay, this one much simpler. This is the 9 over 10. On this axis right here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whereas if we go this way, you got 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's what the continued fraction gives you as far as this kind of behavior. And this is just classical behavior, but the quantum mechanics has the same sort of thing going on in it. And it's worth knowing that this is part of the story for modern physics as it's happening now. Okay, I think we've done enough with the U2, the twofold thing, but I will show just this. This is the polarization idea. You start out with the even state, these are these two phasors that are going to go together, and the odd state, the antisymmetric state, where x and y will be opposite each other. So here's x equal y motion, here's x equal minus y motion. Okay? If you have a calcite crystal or any sort of birefringent object, there'll be a fast axis, a slow axis. Actually, the way we've been doing it, that's the slow axis, that's the fast axis. Okay, but not much faster. We're talking about really small differences in really high frequencies, hundreds of several hundred terahertz. And so it takes a really long time for these two to do this dance here. Goes with the beating and a resonance. But here's a geometrical way to picture it. That you visualize this like we're going to do in relativity. We're going to get on board something that's moving. And you can do that in phasor space. This is a very remarkable thing that most people don't think about. But it's called jumping the gauge, I guess, is the best way to do it. Anyway, I call it the visualization gauge, where we hold the low frequency mode fixed. That is, we get on board it and then see how this one moves relative to us. So here we are with these two phasor hands, one of which we're going to hold still at 12 o'clock, and the other one, that's this guy right here, is going to move. These two are going to move in their motion. That is, this one's going to swing out here and this one's going to swing out there. And that's what we're seeing right here. This one is in just a minute here. That's it. This one right here is that one, and this one is that one. So we're watching their motion relative to this one. So what we get is the high side of the beat. We get this one coming down and this one growing. This is the one that's growing right here. And now you can see you have, because these are equal lengths, you have a parallelogram, and the diagonals are perpendicular. That's the 90 degrees phase lag. Next step, you see, this guy has moved out, and the one that's going the other way has moved to there, okay? Still 90 degrees, always maintaining 90 degrees. So this is the geometry of that magical relationship. This is like I call a very fundamental piece of motion. That is, two waves interfering to do something, to make energy go somewhere. And what has happened at 1/4 of the beat period is that you've turned plane polarization into circular. And you've killed, at this point right here, you've killed, or I should say you start with this one killed, and then you build up to this one, where they're 90 degrees separated. And the 90 degrees, sine, cosine, that makes a circle, you see. And then the next step, this is called a quarter wave plate. You cut off a piece of crystal at a quarter wave plate. You'll get linear polarization into circular. And a half wave plate, if you make it twice as big, you'll get X going into Y, which is, you know, what we've been watching all along here. And then it goes right on through to a 3/4 wave plate, where it turns into right circular instead of left circular. Okay? So here's an example of just plain old simple U2 or C2 symmetry applying to so many different things that are really important parts of our technical as well as just plain old economical life. All right, next step here is the business that has to do with higher end. If 2 was good, shouldn't 3 be better? So I'm going to advance both of these to that situation. And once again, we're going to take a product table for the group C3, which simply has multiplications of an element to the first power and to the second power. And that's what is indicated here. These exponents here, these powers, are a part of the story here, and that's really all the story. And so what I have when I look at this table is a set of matrices. The first, there's a matrix just made out of 1s. Then there's a matrix for R1 that's made out of a 1 here and a 1 here and a 1 there. And then there's what we call a conjugate or transpose made for this third element. And remember, we're counting 0, 1, 2, so third is the thing with a power of 2. And that's numbers modulo 3. And we're going to define all of that in just a minute here. But this is the idea, is that this multiplication table gives me this Hamiltonian matrix. It's going to describe the motion, all the beatings and weird things that a 3 can do, which makes it easy for us to take this right up on to the kind of wave mechanics that we need to do to really understand these subjects. So, here's the base state story. We have a base state that consists of 1, 0, 0, 0. These are the 3 dimensions. 3 dimensions correspond to the 0th one, which is just the 2 top masses here on their equilibrium position. This one's stretched by 1 unit displacement, okay, of mass point 0. And then the unit stretch of mass point number 1, that's the second mass, okay, is gotten by doing a rotation of the first power. That is, I rotate by 120 degrees this activity into that one. Now, by that I mean I leave the mechanics all in the place it is. I put this thing back and then take my activity up to this one, you see. And then I do it again. I put this one back and go over, having taken the activity over to this point. So those are our base states right there, labeled by the elements of this symmetry group. You see how this works? The idea is to make use of really simple multiplication structure and codify it in a good way, a powerful way. Okay? Now, we're using them to label the states, but we're also using them to label what's going to happen. Energy goes from here to there. I'm going to indicate its rate. If it goes this way by r squared, that's what that operation is. Operation by my left hand is a minus operation, and that's the thing that's really important to notice here, is that R1 inversed, R the first power inverse power, is R squared. Again, that's some modular arithmetic where the modulus is 3. So when I say R squared, I mean R to the minus 1 or R to the minus 4 or anything that involves an extra 3. 3 is the highest number here that brings us back home again. Now, you'll see that there is a operator that takes me this way, and there's another operator that takes me that way. And they deserve to have different coefficients in a matrix like this. These coefficients out here can be complex, and that is what makes this really work. But usually, the stuff we're going to do, I'm going to assume real values for all of these. And the stability of the equation that the Schrodinger equation, requires that this guy right here be the complex conjugate of this guy. And once I've said that, I've said it for these two and for these two. So if they're complex, that has to hold. And then the one on the diagonal has to be complex conjugate of itself. That means the diagonal is always real in a Hamiltonian matrix in stable quantum mechanics. Unstable quantum mechanics, all bets are off. That's where you let other states come and participate and then leave. That's a really complicated problem, which is, of course, we're going to have to solve in order to do some of our information stuff, and that's a real bugbear. Anyway, it's the third roots of unity that make this work. Now, just remember the Euler formula. You get the Ix equals cosine x plus I sine x, and put in for x 2 pi times an integer. And then you get this, because the cosine of 2 pi times an integer is just plain old 1, and sine of that is 0. Okay, so this is 1, this number right here. So if I want to take the cube root of 1, this is how why complex numbers are so powerful, I simply take the cube root of 1. That is, I take the 1/3 power of this little e to the 2 pi I over m. Nice trick, right? That is the cube root of 1. One of them, because I can change the integer to some other values. So let's do a picture of this in the real versus imaginary plane. First of all, everyone knew that the cube root of 1 is definitely a cube root of 1. I could cube 1 or quadrate do anything to 1. It's just going to stay 1. But this one right here, you see, has to be taken to third power in order to get back to 1. Remember, if I multiply this by itself, it goes from there to there. That's the square. And then I'll do it again and I get back here. So those are the three numbers that we're working with. Instead of just plus and minus 1, like a binary computer, this would be a trinary computer. Now that's not something that anybody's even talking about now. But at some point, we're going to have the hardware to actually build such a thing. So get used to it. That's one of the applications of this new stuff, possibly. Anyway, here's the minimal equation of that operator. It says 0 equal r cubed minus 1. And there's the three roots with the three factors of this cubic equation, where the rho is one of those three numbers right there. So each eigenvalue of this of the projection operators that we're going to build out of this operator, that is, there are going to be three of the projection operators, each one of them holding one of these numbers, one of these three numbers, 0, 1, and 2, modulo 3. So we're going to, first of all, have them sum up to 1. We know that's what projectors have to do. And then we know that they are the eigenvalues of an operator multiplying that 1. So they're the eigenvalues sitting in their right places. This is all very sneaky, you see. We're letting the operators, we're letting the group tell us the answers. Okay? And then I do it again, I square all of these. So I have to know the squares of these, but that's pretty trivial. You just walk around, or you go the other way by something that, so that the total adds up to 3. In any case, once you have this equation, then you can get the projectors very easily. You simply replace these numbers by their conjugates. And should have noted this really before. The square of 1, that's the square of this, is the 4 pi. 3, that's 2 pi over 3. If you subtract if you subtract 3 pi from that, you get the minus becomes a plus. And that's also called a conjugate. You see, conjugate's when you reflect through the real axis. Very seldom does somebody reflect through the imaginary axis, but that's also an operation that's sometimes interesting. In any case, here are the projection operators that will produce our modes, our waves, as you were. And I prefer to write them so that I use the same numbers as bra vectors if I'm going to do the old-fashioned, bra-ket notation for these things. Now, these numbers, 0 mod 3, 1 mod 3, 2 mod 3, that is literally means m modulo 3 details in just a minute here. But that's the thing that we need to do. So what we're going to do is look at some of the modes and the arithmetic that goes with them. And this is the basic idea of that projector resolution, which I have here, this basic trinary wave function. And this would be an old-fashioned notation here, psi of x, that's used in the earliest quantum mechanics, goes way back to the 1920s. Schrodinger mechanics started to come online. And it's just e to the I kx, but it's got two integers labeling it. And the idea of those integers is pretty much expressed right here. The idea is that when you make a table of these waves, that is, here's position point 0, position point 1, position point 2. Okay, so that's P. P is a good letter to use. Okay, P is position. The thing that's going to be associated with the X, finally, when we have so many of these places, that is, n is really large, not just 3 or 2 that we've been doing, but when we have these huge numbers, this can become a continuous variable, and so is this one. So that's the trouble with quantum mechanics in the way it's presented, is that they start with an infinite number of possible position states. You see, those things just disappear, and they say, there's your wave function. Well, what do you do with it? What do you do? This is going to tell you what to do with it. This is what's going to show you the real guts of the real wave function, real axis and the real values of the wave. The other side of this table is simply the m for, well, momentum. That's what it's going to be ultimately. We're going to prove that using relativity later on. But right now it's just mode number. We've got a mode that's all ones. So all three of these masses are just sort of breathing like that, or if this is in a line, they're just in line like our symmetric mode, which was 0 mod 2. Then there are these two that are sort of analogous to what we had 1 mod 2, but there's 2 of them now. Okay? And each of these two, that's what they actually look like, are settings of phasors that this equation gives. Either the minus 2 pi over 3, either plus 2 pi over 3, and so forth. And generally, the rho is this wave function. What we're plotting here is the conjugate of it. That is the ones that are going with the bras. This is just to make it, you know, a little bit less bookkeeping. We'll see this all in a minute here. But in any case, what we need to do is take a look at what this wave function really looks like, and the other one as well is just the same thing. Now, one thing that I need to do here is set you up so that at some point you can take this into the real actually, take an ordinary textbook. As I said, it's going to be e to the I k x. How do you characterize this this x here? You're going to have some distance between the points here, we'll call that L, and some lattice spacing, that's usually called A. And the idea is that the symmetry number here, 3, times the lattice spacing should be the total lattice length, lattice size, as it were. So that all figures in here. So let's just see that relationship, the relationship between the symmetry number and the lattice length. Now, if we set all these things equal to 1, which is what we're doing here, then we just get 3 for the total length of the lattice. And we do our arithmetic, and then we put that stuff at the very end. And that's a much more efficient way to do these problems and make them pure geometry. In any case, this power P, this position index, defines the oscillation's point, the oscillator's point, 0, 1, or 2. And actually, if you're, well, anyway, I'll say something in a minute later. The power of the operator defines the position. That's another reason for using the letter P, because it's the exponent that we put on these operators right here. That's the power number, and then this is the mode number right there on the projectors. Okay. And that's what this says. And so you're going to have a k sub m that's 2 pi over lambda sub m, and lambda sub m will be the wavelength L divided by m, but it's in a denominator, so I get m over L right there. That's the actual wavelength that you would be using if you just go this the normal way through some book in solid state or whatever that uses this stuff. So let's take a look at what they actually look like. And it has a form, a phase form, that is very, I think we've got it set so it's nice and slow. This is that wave 1 mod 3. Okay. Now I'm going to go ahead on the next one over here and also do an animation that is helpful for looking at these things. I will go ahead real quick right here. It's just, this is wave it, and you can just jump right into the Fourier control here. And there's the wave we were just looking at, kill it, and make any other wave. Now this is a really trivial wave right here. This one, the phasors just go in synchronization. And right now we have 0 frequency for that, so it's not going anywhere. Okay, time is, but it's not. So we're talking about, and that's going to come out of the dispersion function that we're about to calculate over there. So what I will do here is I'll go back to this one and start another one. Let's just for the fun of it, do this one with a minus sign, see what it does, and launch it. Okay. Scales change a little bit when what you see, because what factors we've got. You can, I think, adjust that. But anyway, same wave. It's one wave taking up the full module. This one is a -1 wave. It's coming this way. And if I freeze this thing, I can tell which way that wave's going by looking at who's leading. This phasor is leading that one by 120 degrees. Leading this one, right? Lead gives, right? But this one over here is leading this one by the same 120 degrees. So each of these phasors is forming a triad that's going around in a clockwise manner, that is, left-handed. Okay? This is called three-phase by electrical engineers. Just go out and drive out of the city and look at the towers. There are 3 wires snaking through the sky, right? Each of those 3 wires is one of these phases. So this is just a copy of that one that we'll put there in a minute. As we go forth and make an adjustment on this thing that I think is rather important, and that is give an equal amount of these 2 waves. Now I'm just making it approximately equal. That's probably about as good, and I could read the number and get it, but one of the ways to tell is I've got it 0 somewhere. And then resume that one. Okay, so here it shows both modes that I've turned on now. Okay, and notice that these guys are always opposite, or nearly opposite. It's sitting right here. It's just a little bit shy of where that mode 0 is. And that, where I put the node of this standing wave is gotten by how I adjust the initial conditions. Once I've got them opposite, if I just rotate them both, I can move this along to any point. It's probably a good idea that I didn't quite hit this point, because most of the time when you set the thing, you don't get it right on. But there is a typical standing wave that you would get by simply adding the mode -1 to the mode +1, or the mode 1 to the mode 2 modulo 3. And that's something we have just a few minutes here we need to talk about. Okay, so I'm going to jump ahead on this one real quick here, because here's how you get the what we call a dispersion function or eigenvalue array of the eigenvectors that we've calculated. You simply ask, what is the eigenvalue of the Hamiltonian, which is this thing, in one of these states, these m states. And it's simply equal to this number times whatever r does to that, this one times whatever r does to that, and this one whatever r squared does to that. And that's these 3 numbers right there. So you very quickly, just using the powerful exponentials, calculate a function which we will, this function is valid for any n, not just 2 and 3, which we've already done here, but also 4, 5, 6, 7, 8 on to infinity. Now, as I say, we usually assume real values for these 3 parameters. Stability only requires that they be conjugates across the diagonal, which I'll point out right here. I will, in order to keep this thing having the same amplitude and not involving energy coming in from the outside or leaving to the outside, that this be conjugate to that, and once I've said that, then this is conjugate to that, and this is conjugate to that. Across the diagonal I demand conjugation, and on the diagonal I demand that makes the R0 always real. Okay. So there are the 2 values that this thing has for this particular Hamiltonian matrix. Now, remember that if we're talking about the K matrix, we still have to take the square root of the eigenvalues. If we're doing quantum mechanics, we're done. But for a standing wave or a moving wave of a mechanical oscillator, I've got to take whatever number I get from this box right here, that's the H eigenfrequencies, whatever number I get here, using the different notation, of course, I've got to take a square root. Okay, well, that is the beginning of what is really important and what we're going to be doing in the next class, and that is building and using what we call a dispersion function. Now, this dispersion function only has 1, 2, 3 points, but that function is still there, holding those points and waiting for more. I go to 4, I'm going to have 4 points on those same curves if I'm doing a mechanical oscillator. If I'm doing a quantum oscillator, it's going to be without the square root, and it's going to be a cosine function. And the dots that are on the cosine function, if I go to something that has C100, there's going to be 50 dots here and 49 dots there. So you solved all of the possible wave equations that, well, I should be a little careful about that statement, but essentially for all of the so-called Felix Bloch problems, Bloch waves, B-L-O-C-H, very famous physicist that began this whole theory. So there is a picture of a standing wave, which is kind of what we have right here. But it's just that I've got it moved over just a little bit so that these 2 guys are not quite the same size of each other. But the situation that happens when I add perfectly, and let's see if I can arrange that with this thing in the Fourier control. I'm going to zero this thing out, and I'm going to just start this thing up and make sure that the phase is right at the top. I might as well go up here real big so that it makes a big wave. So I'll start here very close to, see if I can get it right on 3.14 or 159 is what you're really looking at. And then I'll do the same with this one. Is that pretty vertical there? Yeah. If I take the -1 wave and put it up like that, I will be producing that wave, and that's pretty close to what I want to make it look like that particular picture there. Now I've put the node way away from these guys, and I think we're ready to go. We'll just launch that. Okay. So this is a wave where this guy goes around while those guys are out of phase. Don't really need complex numbers for this one. The thing just simply goes up and down. This one is out of phase, 180 out of phase with those 2. So this would be like our antisymmetric mode, except it's 2 of them against 1. Now remember, this one is the sum of these two, this one is the sum of these two, and everything we're doing here involves this incredible, as I say, what makes quantum mechanics sexy, and that is the marriage or whatever of two oscillating phasors. That's the simplest thing you can have, and it's the main part of this theory that we work with. Okay, well, there are other things to say and do here that are interesting, but maybe not so necessary. In any case, you can display any sort of distortion that we talk about here through power laws. And the thing that we're looking at right now is a setting of 0, which is this is called a phonon. When you talk about the mechanical analog of this quantum dot, 3 quantum dot problem, that's called phonon mode for quantization of sound. But the one that involves actual tunneling with quantum dots, that's a block cosine. That is, I think I've got a picture of one of those already here. Oh, that's already into 6. Well, let's go into 6 just to see what we're talking about. There's what it's going to look like for 6. The cosine dispersion function, that's blocks. That's the one that we're using now as we study the oscillation of multiple quantum dots. Or solid-state physics, it's had that for years. It's just that they don't look at the details as much as we do now. Okay, we'll be prepared to do some ruler and compass constructions of the waves and Hamiltonians on Thursday.